right. Well, there is an even simpler method to do that. Rather than doing all this laborious work, we could look at this problem in another way, and it is much more intuitive to look at this second way. So, to see that, notice that let us see what is the length of the path taken by the light in each of the media. So, length, so I would say not another way, but another solution. Well, another, I would say another way to find the solution, right. So, that is more appropriate. So, let us look at the line, the total path length of the two segments along which light travels, right. Length of the two segments travelled by light itself. We see that the total lengths are square root of x minus x naught square. Well, in the first case it is travelling from x naught y naught to x star y star. So, the total length of the path is the following quantity, and the second setup is that the total length is x star minus x 1 square plus y star minus y 1 square, right. So, these are my total path lengths in each of the segments or in each of the media. So, which means my total time, the total time taken by the light travelling from point x 0 y 0 to x 1 y 1, which is a function of y star, which is an unknown parameter, is the total path length, divided by the speed of light in each of the media, right. So, that is as simple as that. So, total length divided by the velocity in each media is going to give me the total time that the light particle takes from going from point A to point B. So, now we have a function which is purely a one variable function, and the one variable is y star. So, now to find the minimum time, we have to differentiate, we differentiate this t with respect to y star to find the critical value of y star, and let us see what happens. So, this becomes, when we differentiate with respect to y star, we see that this is y star minus y 0 divided by c 0 times this particular quantity x star minus x 0 square plus y star minus y 0 square minus y 1 minus y star divided by c 1 times square root of x star minus x 1 square plus y star minus y 1 square under the root, right. Now, let me just recall the diagram here. So, the diagram, let me just go back a slide here. So, notice that this particular quantity, that is what I am showing here is well, we need to see properly. This particular quantity here is y star minus y 0, right. And so y star, and this particular quantity here, which is the length of the path which is travelled by the light, this is nothing but x star minus x 0 square plus y star minus y 0 square. So, notice that this divided by this is going to give me sine of this angle, sine of phi naught, right. So, going back to our slide, next slide again, we see that this particular quantity here which I have circled is nothing but the sine of the angle, or the sine of the angle of incidence, sine of phi naught. So, what we get, well, of course, to find the critical point, we set this expression equal to 0, but this expression is nothing but the following expression, sine of phi naught divided by c naught is equal to minus sine of phi 1 divided by c 1, this is equal to 0, or let me just rewrite this expression that these two quantities are equal. Well, people who have done science in class 12th, they will immediately recognize that this is nothing but the famous Snell's law, right. So, in class 12th we are taught Snell's law, we are just given the expression, but we are not shown how we get this expression. So, what this example shows that the time taken by the light is such that it always follows the Snell's law, right. So, the moral of the story is the following. What we have is that the minimum time taken by light particle, the minimum time taken by the light particles is such that Snell's law is satisfied, right. So, people with a basic science background in high school, they all are familiar with Snell's law, but they do not know how does it satisfy the time taken by the light particles. So, today in this lecture we have shown exactly that, right. So, we can continue this discussion by looking at the various, we can extend this problem as to the path followed by the light in different medias, not only just one media, but maybe several medias, right. So, we have media 1, media, let me call this as media 0, media 1, media 2, media 3, and what happens that in each of these medias, let me call this angle of incidence as phi naught and phi 1, and then phi 2 and phi 3, right. So, in each of these mediums, so for multiple boundaries, the minimum will always be such that Snell's law is satisfied at each boundary, right, at each boundary. Okay. However, what we have seen is we have not exactly used the Euler-Lagrange equations in its purest form. We have broken down the problems into simpler bits and applied Euler-Lagrange equations in each of these bits wherever the solution is continuous, right, and continuously differentiable up to second order, right. So, which means, well, although this problem was fairly simple, in general dealing with kinks or derivative discontinuities is not very easy, and in that case the Euler-Lagrange equations do not work. They do not work because of the underlying assumption of having second order continuous partial derivatives, right. So, in that case we have to use a special result known as the Weierstrass-Erdmann condition. That is a condition of broken extremal, which we will introduce in around the 10th lecture of this lecture discourse. So, we are going to deal with broken extremals in detail, but right now I have just introduced with an example. Okay. So, finally we let us now look at the fourth case of our special case of Euler-Lagrange. The fourth case is the case of degenerate solution, right. So, here I have a functional. Recall that in this case the functional is of the form x0 to x1 a of x comma y, y prime plus b of x comma y dx, right, where I assume that a of a comma b are smooth functions of x and y. A and b are smooth functions of x and y, otherwise we will not be able to apply Euler-Lagrange again. So, let us now apply Euler-Lagrange. If we apply Euler-Lagrange equations, we see that the equations reduces to the following. notice that there is just the linear dependence on y prime. So, my partial of y prime will reduce to only this expression a. So, I get that d dx of a x comma y minus the partial of f. So, this is my small f, this is my small f or the integrand. So, the partial of f with respect to y is going to give me, using chain rule, y prime partial a partial y plus partial b partial y, right, because y prime y only appears in the expressions a and b, right. And we see that well, this is set equal to 0. Notice that we can always reduce this ordinary derivative into partial derivatives. So, this is also equal to y prime del partial a partial y prime plus partial a partial x, right. So, we see that when we strike off this with this, we get the following expression. We see that the Euler-Lagrange reduces to the following neat expression, that partial a partial x, which is this quantity, is equal to partial b partial y, which is this quantity here, right. Or let me just say that ax is equal to by, right. So, in this case my extremal will be such that this particular relation gets satisfied. So, I will not get y explicitly as a function of x, but I am going to get a relation which is satisfied by the extremal y, right. So, let me call this expression by 4. So, there are two observations. So, we say that y is an extremal. In this case, y is an extremal provided y satisfies 4, right. So, this is an implicit equation for y of x, right. Okay. How about, well, this is the case when y needs to satisfy this boxed relation 4. How about a case where this is trivially satisfied for all x and y? So, we can look. So, this is my, let me call this as case, well, let me call this as let me call this as case 4a, where this, if this holds, then 4 needs to be satisfied. We could also have another case. Let me put a big OR and move on to the next slide. We could have another case. Let me call this as 4b, where suppose 4, the boxed expression 4, which is ax equal to by is satisfied for all x and y, right. So, which means that this particular expression, this particular equation is an identity, right. So, it is satisfied for all x and y, then this is an identity, which means that there is no restriction on y. We just cannot find the extremal. However, this particular setup guarantees the existence of another function phi, which is a differentiable function, right. It guarantees the existence of another function which is a differentiable function, right, such that phi of y is a and phi of x is b. Why? Because notice that if we were to assume this expression, we see that phi of y x is ax which is also equal to by, which is also equal to phi of xy. So, if phi is differentiable, then immediately this result is trivial. Phi of yx is equal to phi of xy. The mixed derivatives are equal. So, which means that if this is an identity, the boxed expression is an identity, then there is another phi such that phi satisfies this particular set of two relations, and my f, the integrand, which is a y prime plus b, I replace a by phi y. So, this is phi y times y prime, and b is phi x. We see that this is nothing but the total derivative of phi with respect to x, right. So, in this case my functional j of y, which is the integral of f dx, which is also the integral of d phi, the total derivative of phi with respect to x times dx, which is nothing but the integral of d phi, and this will be from point phi 0 to phi 1. So, this will be phi of x1 y1 minus phi of x0 y0. So, notice that this particular integral is an exact differential, right. This particular integral is an exact differential, and notice that this particular quantity that we have found is independent, it is independent of y of x. So, you just cannot find the extremal in this case, because regardless of y, the functional is always going to reduce to this constant which only depends on the endpoints, right. So, now let us look at an example in this case. So, let me call this as example 5. So, I have that f is f of x y y prime be given by this expression x square plus 3 y square times y prime plus 2 x y, right. So, note, if this is my a and this is my b, note that if I were to evaluate a x, so a x is 2x, and if I were to evaluate b y is also 2x. So, what I get is that a x is equal to b y is equal to 2x, or a x is equal to b y for all x and y, right. So, we see that this is an identity. So, this is an identity in this particular example. So, which means that my functional described by this function f is path independent, functional, and which means that my exact, so all I need to do is to find the exact differential phi, that is the function phi. So, the exact differential phi is given by phi of y. Let us go back one slide. The exact differential is phi of y is a and phi of x is b, right. So, phi of y is a and phi of x is b. So, a is given by x square plus 3 y square and b is given by 2 x y. So, what we do is we integrate with respect to y, and we get that phi of x comma y is equal to x square y plus y cube plus a function of which is purely a function of x. Then when we differentiate with respect to x, we see that this is also equal to 2 x y plus g prime of x, which will also be equal to, using this second relation, this is also equal to b, which is equal to 2 x y, showing that g prime of x is equal to 0, or g of the function g of x is a constant, let us denote it by c. So, which means that my exact differential phi of x comma y is x square y plus y cube plus a constant of integration which is c, right. So, we are almost done here by saying, if we were to look at the functional which is the integral of f dx will be path independent, which is nothing but from x0 to x1 of d phi, which is nothing but phi of x1 y1 minus phi of x0 y0, which is all I have to do is to substitute the value of phi at x1 y1, and we just cancel out the constant of integration, and minus x0 y0 plus y0 cube. So, regardless of the function y, I am always going to get the value of the functional to be a constant which depends only on the final and the initial points, right. So, finding the extremal in this case is a useless exercise, right. So, what I have done is the following. So, let me rewrite this entire exercise in case 4 in the form of a theorem. Let me state the result in the form of a theorem, and this theorem is simple enough so that we can also give a quick proof to this result. So, I denote this theorem by theorem 3. The theorem says that suppose the functional j is integral f dx has extremals, the integral j has extremals with continuous and smooth derivatives, right. So, this will be the final result in our lecture series. So, j has extremals with continuous smooth derivatives up to second order, right, and well, extremals up to second order such with, well, I forgot to mention the extremal is an extremal with fixed endpoints. So, we are still looking at fixed endpoint problems, right, and such that the Euler-Lagrange equation reduces to an identity. It reduces to an identity. Then what I have is that the integrand of this functional, this integrand f must be linear in y prime, right, and the value of the functional is independent of y, right. So, what I have said in this result is the following, that whenever the Euler-Lagrange, this is the most important part of the statement, whenever Euler-Lagrange reduces to an identity, it necessarily going to give us the case 4, that is, the integrand will always be a linear function of y prime, right. So, this is as if we are saying that an identity in the Euler-Lagrange will if and only if with a necessary and sufficient condition will lead to the case described by the case 4, right. So, let me do a quick proof before we end our lecture session. Suppose let us assume that the Euler-Lagrange equation is an identity. The Euler-Lagrange equation is an identity, right. So, which means that we have the following equation satisfied for all x y, right, d dx of del y prime is equal to 0 and this is satisfied for all x y, since Euler-Lagrange is an identity. Now, let me rewrite this expression using chain rule. I get that this is partial f partial y minus partial x partial x of partial f partial y prime minus second partial derivative of f with respect to y and y prime minus partial f partial y prime square y double derivative, and of course, this is equal to 0 as we have shown on the left hand side. Now, we are doing a problem in which f is a function of x, y and y prime. So, the maximum derivative argument that f has is only up to first order, which means that the only term which contains the second derivative of y is this following quantity, and since we do not have any terms involving second derivative of y, right, so what I am saying is the following: since y prime appears only in the last term, right, and f is only a function of x, y and y prime, which means that there won't be an explicit appearance of any terms involving y double prime. So, which means that the coefficient of y double prime, which is second partial derivative of f with respect to y prime, this is equal to 0, right. So, that comes from here, right. So, from here I can directly deduce that f of x, y, y prime is a linear function of y prime, right. So, that comes right away, and further, so I have set this equal to 0, which means that the rest of the quantities will also be 0. So, further, since I have, so I am just rewriting this remaining quantity. So, partial f partial y minus partial x of partial f partial y prime minus partial 2f of partial y prime, this is set equal to 0, and when we replace f by this quantity a y prime plus b, we are going to get the relation a of x is equal to b of y. The derivative of a with respect to x is equal to b of y, and this is satisfied for all x in x0 x1 and for all y in the set of second order continuously differentiable functions satisfying the boundary condition. So, the moral of the story is, whenever we have the Euler-Lagrange equation being an identity, we always have that the integrand is a linear function of y, and that the Euler-Lagrange equation finally reduces to this neat expression Ax is equal to By. So, thank you for listening. In the next lecture, I am going to talk about certain other topics related to Euler-Lagrange, namely the invariance, the existence, uniqueness and further generalization of Euler-Lagrange equations. Thank you for listening. Thank you very much.